Okay, let's take a look here at section 6.3, exponential equations. So we're going to use what we've shown in previous sections about exponential functions being one-to-one to solve these things, or we're going to use what we learned about properties of logarithms in the last section. So yeah, we're going to have steps to do each of these things. So first we want to get the exponential stuff alone. So yeah, isolate the exponential functions. So like looking at this one here, those exponential functions are isolated, right? So we don't have something going on here like a +1 or something else. If it's convenient, we want to write both sides with the same base. So then we could say the exponents are equal, right? Because we had this property in the last section, right? If I've got two bases, they're the same, being raised to do different or possibly different exponents. If that's true, then those exponents have to be the same. And this came exactly from the fact that the exponential function was one-to-one, right? So this is just another way to phrase what one-to-one means. Okay, otherwise, if we can't do that, we're going to end up taking the natural log of both sides, right? Remember, if I have some number here raised to a power, and if that's inside a logarithm, then I can take that exponent and write it as a factor, and then that piece is no longer in the exponent position, and we can operate with it. So let's see some examples here. So first one, we want to do the steps, right? So isolate the exponential functions on each side. That's already done, right? 2 to this power is equal to 2 to this power, or excuse me, 16 to that power. Well, what we want to do here looks like A. So if we can, we want to rewrite 16 as a power of 2. So we know that 16 is 2 times 8, which is 2 times 2 times 2. So this is 2 to the 4th power, right? 16 is 2 to the 4th, right? And we can use that fact here. So the left side doesn't change, but we can rewrite that 16 as 2 to the 4th. So here's going to be the hard part, is remembering what we do with exponents, right? Exponent rules. So we know that when we raise a power to a power, we multiply. So we've got on the left side, that didn't change. But on the right side, this will change, right? Because this is 2 and then 4 times 1 minus x. So now we have it written as 2 to some power equals 2 to some other power. That means we can make those exponents be equal, because they have to be, right? Because this is one-to-one. And now we can just solve this in the usual way. We can maybe multiply that 4 through here. So we got 4 minus 4x. And then I've got 3x is equal to 4 minus 4x. If we can add 4 to both sides, add 4x to both sides, we'll have 7x equal 4. And then divide by 7, we got 4 over 7. So we come up with x equal 4 over 7. And just like with other equations, we can absolutely just plug this number on in there and see if it worked, right? So to check this, we would plug it in, right? 2 times 3 to the 4 sevenths. That would be 2 to the 3 times 4 is 12 sevenths. Okay, so that's the left-hand side. And then the right-hand side, we would have 16 to the 1 minus 4 sevenths. So that would be 3 sevenths. And then we remind ourselves that 16 is 2 to the 4th. And in fact, we do have 12 sevenths. So that's the right-hand side. So it worked, right? They're the same, right? This is the same as, this is the same as this. Okay, cool. So we plugged it in and it made it a true statement. And we go on our happy way. So we can do the same thing here, right? We want to first isolate the exponential function. So I want to get that thing alone. Well, if we want to get that thing alone, it's being multiplied by 1,000, right? So I can divide both sides by 1,000. And 2,000 divided by 1,000, that's 2. And we got 3 to the negative 0.1t. Okay, so now these bases are not the same. So we could, if we really, really wanted to, we could use the change of base formula from the previous section here to rewrite this with a base of 2. But the easier thing to do is to use the one-to-oneness of the logarithm function to just take a logarithm of both sides, right? If I've got two things that are equal, that means that the logarithms of both of those things have to be the same, right? And that works in both directions. You know, this is an if and only if statement, right? Remember this one-to-oneness. All right. Anyway, so we can apply the logarithm to both sides now, and the convenient thing there is now I've got that in an exponent position with my logarithm. So now the left-hand side stays as natural log 2, and then we can tack that exponent piece in the front as a factor. All right, that's awesome. So I don't know, I'm more comfortable with fractions here, so I'm going to rewrite that as negative 1/10. So we can rewrite this as negative natural log 3 over 10, right? Well, there's a t there, isn't there? Let me write that in a better way. So negative 1/10 t times natural log of 3. This is just rearranging this. We can write it as negative natural log 3 over 10 times t, right? Just rearranging it so it's got the number part and then it's got the variable part separate. So on our left-hand side, we got natural log of 2, and on our right-hand side, we've got negative natural log 3 over 10 times t, and now we can solve for t. So we will just multiply by the reciprocal of our fraction there, and that's going to make it go away on that side. And we can't forget we have to multiply by the reciprocal on that side, the left side as well. So on the left-hand side, we're going to have negative 10 natural log 2 over natural log 3 equals t. There we go. So yeah, we have our exact solution here. And I mean, of course, we can crank the numbers through a calculator and find a decimal approximation for it, but this isn't the point, right? We want the exact value, and we've found it. And we can do the you know, plug it in and show that we get 2,000 if we plug that in there. And maybe we could leave that as an exercise for you to do. Just plug that in there, see if you get the same thing. Okay, great. That was the second one. Third one. Okay, so this, we want to isolate the exponential parts on both sides. So this on the left, or excuse me, that's the right-hand side. On the right-hand side, that's good, but on the left-hand side, that's not one exponential function, right? We want to write it as one base and one exponent. So what can we do here? We know that 9 is 3 squared, don't we? So we got 3 squared times 3 to the x equals 7 to the 2x. And that's good, right? Because now we have the same base. Now when we multiply those, we know that the rule there is that we add the exponents. And now we're in good shape here because now we can do the same trick we had on that previous problem. We can do a natural log on both sides. And that makes it so our exponents are no longer in the exponent position. Right, we can move those down. All right, now comes the hard part. We're still solving for x here. We want to get x alone. So we want to get x on one side of this equation. So we probably want to distribute this. So we got 2 natural log 3 plus x natural log 3 equals 2x natural log 7. So we want to get the x stuff alone. So let's take and move this to the other side. So we got 2 natural log 3 equals 2x natural log 7 minus x natural log 3, right? If we subtract this piece from both sides, that's what we would have. And now we can factor our x out of there. and we're left with 2 natural log 7 minus natural log 3. And now we're home free. We can just divide by that piece now. So we got 2 natural log 3 over 2 natural log 7 minus natural log 3, and that is x. All right, cool. And again, we can plug that in and show ourselves that it works. What we could also do, and part of some confusion that might exist, we can use properties of logarithms to clean this up a little bit. Now, if we're just asked to find the solution, we've done it and it's over. But if we're asked to maybe write it as one logarithm or something like that, that might not be as easy of a task, but we can sure simplify it. And we might relate this to like, I don't know, rationalizing the denominator of a radical, or simplifying a complex fraction, or it's one of those things that it's more of a stylistic requirement. Like we don't want it to look so ugly, so we can make it not look so ugly, right? We know that if I've got a number in front here, I can add that as an exponent. So instead of 2 times natural log 3, I can have natural log 3 square. And then the denominator, instead of 2 natural log 7, I can have natural log 7 square. So that's natural log 9 over natural log 49 minus natural log 3. And now I've got a difference here, which we could write as a quotient, right? So we would have natural log 9 over natural log 49 over 3. And I mean, if we want to, we can use that change of base formula backwards and further write this as log base 49 over 3 of 9. If we want to write this as one logarithm, there we go. But just to be clear, this is good right here. What we had to start with is fine. But we can use our properties of logarithms to rewrite these things if we really, really want to. Or if we're constrained in a certain way, we want our answers to be of a certain form. But if we can get to this is what's going to be acceptable for us in an exam or quiz type situation. Okay, cool. Moving on. All right. So this guy, we got 25 to the x power equal 5 to the x plus 6. Okay, so we can just let the cat out of the bag right away. These are going to be a special class of these problems that we may, we've seen this type of problem before, but it's in disguise. So let's rearrange this here. Let's put everything on one side, because no matter what we do here, I'm going to add these things together. We're not multiplying them, so we aren't going to be able to write that with one base, and that's kind of unfortunate. But here's the trick. Let's get everything on one side first, right, and 0 on the other. Now I can rewrite that guy as 5 to the 2 to the x. And we can rearrange this, right? We know when we raise a power to a power, we multiply these, and we know that multiplication is commutative. So if I wanted to write that as 5 to the x square minus 5 to the x plus 6, well, we can do that, right? So now hopefully this looks familiar. If we say that 5 to the x is some other variable, say we don't want to use a Greek letter, let's u, then what this looks like is u squared minus u plus 6 equals 0. And that is a quadratic equation that we can solve pretty quickly. We're going to solve that probably by factoring if we can. So we want 2 factors of 6 that add to be negative 1. Oh, okay. I can see that we can't factor that, and now I immediately see my error. So when we moved these to the other side, we had to subtract them from both sides. So here's the error that I made. These should all be pluses. So hopefully you caught that in your work. We caught it here, so we're good to go. All right, so now we've got this, and we can factor this. So we do. So we got u, what do we want? Minus 3 u plus 2 equals 0. And now we can say, all right, u is either I guess, not skipping that step, we got u minus 3 equals 0, or u plus 2 equals 0. So that means u is equal to 3, or u is equal to negative 2. And then we remind ourselves, we're not looking for u, we're looking for x. So we need to substitute back, right? So 5 to the x is equal to 3, or 5 to the x is equal to negative 2. And now we can solve these both individually. The one on the left here, we're just going to do the same thing we did with the previous two examples. We're going to do something else with the one on the right. So let's deal with that just in a second. But this guy, that x can now be written as a factor instead of an exponent. And we got natural log 3 there. And then we can just divide by natural log 5 on both sides. And we're done. And we can also write this as using that change of base formula. This would be log base 5 of 3. And we're done. So something of note here is that at this step, before we did that natural log of both sides, we got 5 to the x equals 3. So if we have something like this, we can just immediately rewrite it with logarithms, right? So x is the power we raise 5 to get 3. And then, it's the same thing, right? Great. So what about this one on the right? We can make an appeal to maybe what we've done in the past. This thing here, remember this is an exponential function, and the range is 0 to infinity. So it does not include negative 2, so it can't be negative 2. So this tells us that it has no solutions. And the only solution is this one. Now, maybe we didn't recognize that, and that is entirely possible. And what if we didn't? So if we tried to do that natural log bit on both sides, we would end up saying something that can't happen, right? So we would have x natural log 5 equal natural log negative 2. So then x is natural log negative 2 over natural log 5. But we know that this thing is not a real number. So we discard it, and it's not a solution, right? And we made the same conclusion here, just with a different kind of frame of reference there. Okay, good. One more. Yeah, this one looks sort of uglier than the rest, and we want to fall back on what we already know and are already strategies that are already solid in our minds. So whenever we have fractions, we want to get rid of the fractions, right? So getting rid of the fractions here, if we multiply both sides by 2, right, we would get this if we multiply both sides by 2. And now we want to get rid of the fraction that doesn't really look like a fraction, right? So e to the x minus, this is 1 over e to the x, isn't it? Okay, so now it's still got fractions, and we want to get rid of fractions. So as long as e to the x is not 0, and we know it's not 0 because it's 0 is not in the range of that function, so we know that that's not 0. If we multiply both sides by this, well, what happens? This side multiply through, we get e to the x times e to the x, so that's e to the x squared. And then we have e to the x over e to the x, that's 1. And then we've got 10 e to the x. And now this looks an awful lot like the one we just had, doesn't it? So we got e to the x squared minus 10 e to the x minus 1 equals 0. And now maybe we can make a substitution. So let's say u is equal to e to the x. And we can put that in there. So we got u squared minus 10u minus 1 equals 0. And now we can solve for u. All right, so let's do that. This one we can't factor that, which is unfortunate, but we do have the nice quadratic formula, right? We can say that that's negative, so u has to be negative b, right? We got a, b, c. So negative b would be 10 plus or minus the square root of b squared, so that's 100, minus 4 times a times c over 2 times a. So we've got that u has to be 10 plus or minus the square root of, what is this, 104 over 2, and we can simplify that, can't we? Isn't that 4 times 26, isn't it? So we can say 10 plus or minus 2 square roots of 26, right? This is just simplifying that radical. And we got over 2, so that means that's 5 plus or minus square root 26. Okay, so we got u is equal to this. Well, we don't really want u, we want e to the x, right? Making our substitution back. And now we've got two things, right? We're breaking up into two statements. So e to the x is either 5 plus square root 26, or e to the x is 5 minus square root 26. Now let's think about this in the context of what we just did here, right? Well, I mean, maybe not exactly that, but this one, right? So 5 to the x equal negative 2, that cannot have solutions because we know that 5 to the x is either, well, it's bigger than 0. So in particular, it can't be negative 2, right? Because that's less than 0. So that means that we can say the same thing about this one, right? Because we know that the square root of 26, that's bigger than 5. So that means that this is negative. So no, it can't be negative. So e to the x is always positive no matter what. And we're saying, well, one of the options is that it's negative. Well, it can't be negative, so we just discard that one. And now we can rewrite this guy. Either immediately rewrite it with logarithms. We can say the power that I raise e to, if I want to get 5 plus square root 26, that's got to be our x. So natural log 5 plus square root 26 is x. So there we go. Or if we're over here, we can take a natural log of both sides. Let me write that. E to the x equal 5 plus square root 26. We could do the natural log of both sides business, and then we're going to have pretty much the same thing, aren't we? So this would be x times natural log of e equal natural log 5 plus root 26. Well, we know that natural log e, that's just 1. So x is natural log 5 plus 26 under a radical, which agrees with what we just had there. So happy days. Okay, so yeah, things to look out for, I guess, are what we had with this one, right? If we end up saying that an exponential function has to be negative, that can't be a solution. That can't be true, right? Because, well, appealing to the graph of e to the x would look something like that, and all of these values are positive. Okay, great. So we've just solved a bunch of equations involving exponential expressions. So great, that's it. So thank you for watching the video, and have a great rest of your day.